Alright, so this is the weekly problem in which we have a 4-meter high, 5-meter wide wall that has long 15 centimeters by 25 centimeters cross section horizontal bricks separated by 3 centimeter thick plaster layers, as shown on the figure to the left. Right, so we have the brick here is 15 centimeters by 25 centimeters, and then it has 3 centimeters of plaster separating each brick. So that's the 1.5 plus the 1.5. This makes the 3 centimeter. There's also a 2 centimeter thick plaster layer on each side of the wall and a 2 centimeter thick rigid foam on the inner side of the wall. So we have plaster over here, that's the plaster he's talking about, and the plaster over here on each side of the brick, and then we also have a foam, which is this orange fella there. The indoor and the outdoor temperatures are 27 and minus 5 Celsius. So since we know the foam is an inside from what we just read, that's going to be 27 indoor and minus 5 outdoor. Which means that we can already know that Q is going from this side to this side here, right? It's one thing we know already. Assuming one-dimensional steady-state conductive heat transfer, determine the rate of heat transfer through the entire 4 by 5 wall. So if it's one-dimensional heat transfer, it means that we're ignoring any heat transfer that's occurring in this direction or this direction here. We're only concerned about this one that's happening on this one here. We're not concerned about the ones going inside or anything like that, right? So only one direction. Now, if there's a difference in temperature, we know there'll be a, that's the driving force for our heat transfer. So therefore, we know there'll be a Q and an R, right? And the R is the thermal resistance. So what we can do is we can find the Q, which is what we're after, by dividing the difference in temperature by the equivalent R for the whole thing. Since we have different parts of this thing, we're going to have to first create a electrical equivalent circuit, and then with that circuit, then we can go ahead and do one single R for the whole thing. Now, the difference in temperature in this case here will be the 27 minus the minus 5, right? So that's a 32 centimeters degrees Celsius difference in temperature, or in Kelvin, because it's different temperature, so it's the same thing in terms of quantity. Okay, next thing we can do is there's plenty of different ways to solve this question, but I'm going to show you the one that I find to be the easiest one. What we know is that there's a little pattern that repeats, right? So let's break down that pattern. It's actually shown on the drawing. There's this little pattern over here that repeats itself over and over and over again, because this wall keeps going. You can see the drawing is showing that the wall does not end here, right? It keeps going, and it goes all the way to a 5-meter height, and it has a 5-meter width. So the perpendicular area through which Q is coming through is this big area here of 4 times 5 equals 20 meters squared. That's our full area through which heat is going, right? So there's different ways you can approach this. Now, one of the ways is to think, okay, but if this little pattern here, how big is this pattern? Well, this pattern is something like this, and it's 28 centimeters in height, right? So that's a 3 centimeter plaster plus the 25 centimeter brick, and it's what is that? 28 centimeters over a 4-meter height wall. So that means that we do 4 times 2 centimeters divided by 28 centimeters. I'm gonna get 14 point something. I don't remember. 14 by 0.3-ish. Okay, so that means that this pattern, this green pattern that I just drew, let's get rid of this chunk. I'm going to leave that. Let's get rid of this. Okay, so this green box here is going to repeat itself 14.3 times upwards and downwards. All right, on the total thing. All right. But I think the easiest way to solve this, and again, there's plenty of ways you can do it this way, that's fine, but the easiest way to solve this is actually to come up with a different box, right? So the box that I like to come up with is this one here, which is the same pattern if you notice, but the difference is now, instead of having a plaster on top and one on the bottom, I just have a plaster that's twice the thickness, right? And then instead of having a circuit that I have 3 in parallel, now I only have 2 in parallel. So that makes it easier. But just like I can do that, the other thing I can do is I can transfer this plaster from this side to this side here, and just have double the thickness over here in plaster, which is going to be exactly the same thing. It's just going to be, in terms of heat resistance, that's the same thing. So we can simplify this into a simpler version of this wall that will have exactly the same thermal resistance and make our lives easier. So I drew that in the bottom here, the little drawing of what that will be, right? So I just got, remember, there was a plaster on this side, and I threw it together here, so I have double the thickness in plaster, and the plaster that was on top, now I'm just thinking of them, the both of them together, like that. Okay, so this is exactly the same thing as the one on the top figure in terms of heat transfer, and it makes our life easier, because now if you notice what we have here is we're going to have one resistance, that's my R1 that I drew here, let's put it on the top. I have my R1, which is due to the foam, then I have my R2, which is the blue one, due to the plaster that's on its own, and then we're going to have a system in parallel, which we're going to have R3, which is going to be because of the brick, due to the brick, and on the bottom R4, which is due to the plaster. So I just transformed something that would have otherwise 6 resistances into something that only has 4. Right? And then how do I know that's parallel? Well, we're going from this side to that side. So I need to go through the foam, there's no other way. I need to go through the plaster, but once I get here, I have an option of going either through the brick or through the plaster. Right? So because the heat can choose which way to go, that's a system in parallel. Okay, so what will be the area for these guys? Well, R1 and R2, they're going to have the area that we just, for this little pattern that repeats, right? It's 28 centimeters in height, and then I can choose whatever width I want, right? I put 1 meters down here because it's the easiest one for us to work with, but we can choose whatever we want. We could have gone and put 5 to start with, which is the final one, and that will be fine, 100% fine. But since we're already doing something on a smaller scale, it's probably in our best interest to keep this on the unit scale, make our lives easier on the math, and then we just account for both these things by the end of it. But again, there's so many different ways you can solve this. Okay, so in terms of area, so let's think about these areas here. So in terms of area, when I'm doing the area for this small unit that repeats itself, the area for R1 will be, let's look, it's going to be just this whole thing here, right? So this whole chunk here for the foam. So something like this. If I'm looking downwards, it'll be something like this. 28 centimeters in height, 1 meter in width. So that would give me a 0.28 meters area. So R1 would be 1 times 0.28. That's 0.28 meters squared. R2 will have the same as R1, right? So this is 0.28. Right, which would be, let's draw it quickly here. I can delete it afterwards. Right, we're talking about this area here for the plaster. Just that one just there. But then R3 and R4, they have different ones, right? R3, which is a brick, will have something that will be like so. We're going to have a 25 centimeters here on the side, and 1 meter as the width. Right, and if I look at that, it's going to be a 0.25 meter squared area. And the plaster, the last one, the last plaster, R4, well, that's only going to be, well, 0.003, so 3 centimeters on its height, which is this guy here, painting in blue that you can't see probably, but this guy here, over there, and the same with this everybody else, right? So this area is 0.03 meters squared. Okay, so I can calculate what's the resistance for each of these guys. I'm going to do resistance for R1, R2, R3, and R4. I have these areas here for them so that I remember as I go. And what is the game plan here? Well, the game plan is, let's make an equivalent circuit. This equivalent circuit will be R1, R2, and an R equivalent for 3 and 4, right? I'm going to transform that parallel into an equivalent if it were in series, and then I can have, again, an equivalent circuit, which is R total, let's call it, which is just going to be the sum of all these guys here. And then once I have that one, this one final one, I can go back to this idea here, and I can plug in to there, that final resistance. I already have a difference in temperature, so I can find my Q. Okay, so what are the resistances? Well, one by one I have them here, so the R for the foam, I have the thickness of the foam, that's 2 centimeters. K for the foam, 0.026, and the area for the foam, which is the one that we just figured out just here, so this guy here, 0.28. Okay, so that's going to give me 2.75 Kelvin per watts. The one for the plaster is over here in blue, so twice the thickness of the plaster, because we put both plasters on the same side, so instead of having 2 centimeters and then plus 2 centimeters, I'm just going to have 4 centimeters. K of the plaster, and the same 0.28 meters squared for the area. Then we get to the brick, and we need to recall that the area on the brick is the 0.25 instead of the 0.28, right? So the brick has it has 15 centimeters in thickness, 0.72 K. And the plaster that is underneath the brick will have that smaller, even smaller area, right? This area over here, the 0.03 meters squared. It has the same thickness as a brick, and it has the same K as the plaster, R2. Now, notice that a couple of things to compare here when we get to this point is, let's first compare R2 and R4. Okay, they're both plaster, they have the same K. But our R4 has way more thickness, and we know thickness is proportional to the resistance. And our R4 also has a way smaller area. So it's much harder for heat to go through the 0.03 meters squared than it is to go through the 0.28 meters squared. So therefore, that's why the difference in resistance is so big from R2 and R4, in spite of them being the same material. Okay, and the other thing to compare is then R3 and R4, because they're a system in parallel, right? So that means that when the heat, like we said, right, when the heat reaches this point here, it's coming through, and when it reaches this point here, it can split up and choose pretty much where it wants to go. And it's so much easier for it to go through the brick than to go through the plaster. So when we get the equivalent, when we find this guy here, the equivalent for 3 and 4, it should be somewhere way closer to the brick, which is just like a highway, open avenue for it to heat to go through, than to the plaster, which is something that is hard for it to get through. It's like a hard road to go through, right? So we know the equivalent will be just the sum of both of them inversed, and that renders about 0.803 Kelvin per watts. And notice that this is indeed not only is it closer to my R3, but it's actually smaller than R3 and nowhere near my R4. Okay, so it's from the point of the perspective of the heat, it's much better to have that open avenue there and actually have the option of going through the plaster too, right? It's the best thing to do. And then once we get to this equivalent resistance, what we have now is a system like so, right? The 3 resistances are all in series. So to find what's the equivalent one for all of them, we just need to sum them all up. So we're going to be summing up the 2.27, the 0.65, and the 0.8. That's going to be our sum. And our sum turns out to be, where is it? Down here. Summing them all up. 4.204. So that's the equivalent. Okay, so that's the equivalent of having this little system like I drew here. Okay, so if I have 27 on one side minus 5 on the other side, and I have only a single resistance that mimics the whole wall there, or actually that pattern of the wall, the unit, then I can find what's the Q that goes through there. And then I can go back to that equation that relates R and delta T. We have both those things, we plug them in, and we get 7.612 watts. Now, remember that this value here is the amount of energy that goes through the pattern, right? So this is the amount of energy that goes through this little guy here. Where is it? It goes through this little guy here. But this little guy is not the whole wall. This is just a part of the wall, right? And in fact, this is only 0.28 meters squared when the actual has 20 meters squared. So there's a couple ways we can go about this now. One of the ways is, like we said before, we can notice that this is going to render this the 4 meters over the 28 centimeters is about 14. So this pattern is going to repeat in height 14.28 times. So we can multiply that number by 14.28 and then multiply that by 5 to get the appropriate width. That's one way to do it. Another way to do is that we can note that because Q is proportional to A, okay, it's a linear proportion. In other words, if I double A, I'm going to double Q. If I have A, I'm going to have Q, and so forth. That means that I can just do a proportional idea here, right? So if my 7.612 watts is for a 0.28 meter squared area, then for a 20 meter area, I'm going to have the unknown. So I just do 20 times this divided by this, and I get that. That's one option of doing it. The other one is actually doing the whole way of thinking, which is, okay, 7.61 watts is for a 0.28 meter watt, right? So if I divide one by the other, I'm going to get 27.2, which is equivalent power for every meter squared. But since I have 20 meters squared, I need to multiply this by 20, and then by multiplying by 20, I'm going to get 543. So 543 watts is the total energy that goes through this 20 meter squared wall. Okay, so in other words, what have we found? We found that for this fella here, for this, so for this fella here, what will go through it would be 7 watts-ish, right? About 7.6 watts. But since this fella repeats itself a lot in a wall like such, that means that on this big wall here we would have 540-ish watts going through. Right, so that's about it for this question. So just a little bonus content for you guys. One thing that's important to note, and I'm not sure if everybody notices, is that we're dealing with one-dimensional heat transfer, right? So we're going from only considering the heat that's going from this side to that side. And if you think about it, what we're doing is, because we're considering only one dimension, this guy, we're doing 1 meter, but we're considering this brick to be 1 meter long, right? And the plaster to be 1 meter long, and so forth, on this direction here, right? On this Z direction here. And the wall, when we do the 5 meter wall, it's the same thing, right? When we do the 5 meter wall, all we're doing is making this 5 meters wide, and therefore the brick is 5 meters wide. It's just a really freaking long brick, right? So in this direction, it's just a freaking really long brick. It's still like 28, not 25, right? The brick was 25. So it's still 25 centimeters high, but it's 5 meters wide. Right? So it's a big fella. Okay, so this obviously, if you think about like real life and stuff, it wouldn't be compliant. It would not make sense in a way. But that's the reason why we keep saying the statement of the problem says it's one-dimensional. We're considering only on one-dimensional. Because if you think about it, what we'd have to do in, like, say, if we were a real wall per se, what we would have to do is What we would have to do is we would have to consider probably there's going to be a little gap here, over there, and then I'm not sure what if the gap is going to be plaster or whatever that is, and then we're going to have the brick again, like that, and then have the plaster again like that. Alright, and then it continues itself, and then what would happen is it would have another pattern that's repeating itself in this direction here too. And if you think about heat coming through, what heat was going to do is, as it's coming through here, it would come here and then it would split to this side and this plaster, the same way as it's splitting on this plaster and this brick here. So you can see how that can be complex to the point where it's exponentially complex in terms of the way that we need to relate the things that are interacting for us to solve it. Okay, so again, that's why it's considered a one-dimensional one, because then it doesn't really matter what is over here on this side, because you can see this brick to be just a really long fella that is 28 centimeters high and 5 meters wide. Okay, so probably good to keep that in mind.